Thank you very much.
Well, thanks so much, Max, for a beautiful introduction. And hello, everyone. Welcome, everyone. Also, thanks to Giovanni. He was just online 3 seconds ago, but now he disappeared again. And of course, also Garrett for organizing this brilliant masterclass series. And yeah, it's a great honor and a great pleasure to do one of them. I'll be talking about path collector variables, and I assume you already know a little bit about them, and that's why you came. But maybe not. I am quite open to well, any level interactions and questions about this topic. So, we're actually with quite a small crowd, 11 participants, so including Max and myself. Which means I think we can do this quite interactively and informally. So you're all very much invited to ask questions whenever you want, right? So if you want to ask a question, just unmute and start talking, and yeah, I should hear you, and we will talk. I probably have way too many slides. I'm supposed to talk until 5. It's already 4:10, I think. But then Max told me that I can just keep on talking until no one is here anymore. So let's see how that goes. I'll try to, focus a little bit. Depends also how much questions there are from you guys. And let's see. So this, let's talk about path collector variables. So I'm gonna start with just a very brief outline of what I'm going to talk about in the next hour and a bit in 5 slides. So what am I going to talk about? So first, why I am interested in path collector variables, and maybe why you could be interested in path collector variables. And what you see here are 2 examples of simulations that we do in Amsterdam. On the left-hand side, you see a cluster model of the catalytic side of an enzyme. It's called hydrogenase, the hydrogenase enzyme. It has 2 iron ions here, and then actually there's a cluster of irons and sulfurs here as well. And this thing is very efficient to make hydrogen molecules from protons and electrons. And there's quite a few steps. The protons come from the right, and the electrons come from the left. And you need at least 2 protons to form H2, which is formed on this side here on iron. And there's actually quite a few collector variables involved in this transformation. So this is, of course, an activated process, not highly activated, because it's a good enzyme. It's very efficient, but still slow on the time scale of DFT. MD simulations, so you won't see anything happening on the time scale of tens of picoseconds. And so, but there's several bonds being formed and broken, right? So this hydrogen forms a hydride that forms a bond with this iron, then there has to be a bond formed here, and this jumps around, etc. And so what we use these path collector variables for is that we sort of know in this sort of chemical reactions which bonds are being formed and broken, and so we can make a list of them. And so here you see 4 of them, and as I move, if the reaction progresses along some internal reaction coordinate from reactant state, which will always be 0 in my path progress variable, to 1, which is the product state, these things change, and I try to calculate the free energy profile along this path progress, right? And though in school we always learn to write reaction coordinates, but some people in this community get nervous if I say I'm using a reaction coordinate, because I'm not supposed to know what is the reaction coordinate. So that's why we talk about collector variables and stuff. So I'm writing path progress or reaction progress. Maybe sometimes I still write reaction coordinate. So this is one example. So we use sometimes DFT based molecular dynamics simulations, which are slow, right? And so I need a method to do enhanced sampling to find the reaction path of all possible bonds that are being formed and broken, or collector variables that I can think of. It should be fast, it should be very efficient, and I want to sample free energy landscape as well. Here's another example, which is it's with a QMMM So partly density functional theory, partly force field simulation of an enzyme. It's a photoactive protein called blue light using flavin, and there's a flavin molecule here that can catch a blue light photon, and then some stuff is happening. There's an electron transfer coming from this tyrosine, and then there's a proton transfer from this glutamine, and then the thing rotates, and there's some proton transfer happening, and eventually that signal. So there's there's a cascade of events. So electron capture, electronic excitation, electron transfer, proton transfer, chemical rearrangement, and then finally a change in the protein structure. And all this stuff has to happen in a cascade. So again, pretty complex, many collective variables involved, and we would like to calculate this free energy landscape. So that's systems that use DFT. So timescales, so simulation scales are going to be short, and so I need something efficient. But we also look at force field simulations of biomolecular processes, for example, and you'll see some examples stopping by. But in those cases, it's even more difficult to come up with initial collective variables, and path collective variables can help. So how does it work? So in a nutshell, we have two stable states in a space of collective variables that I should have chosen beforehand, and I can think of a path that goes from A to B, which could be some sort of average transition path, and all trajectories that go from A to B or vice versa will pass in the neighborhood of this guess path, right, or at least of this average transition path. And maybe this is a minimum free energy path of some channel, and there could be other channels as well, right? So maybe there's other reaction mechanisms, and this path will pick one of them. And the trick, the idea is, to find that path. So can we describe this path as a string of nodes, right? So we have a bunch of nodes here that are connected, and we start from some guess path. We do a bias dynamics using some enhanced sampling method. And then we have to move those nodes on the fly to the mean, to the average flux, let's say, transition flux, and we then there's some reparameterization happening. So that's in a nutshell the method. It builds on previous work of many people, including so Erik van den Einde, of course, is a person that has worked a lot on these sort of methods, the so-called string methods. At the same time, another method called nudge elastic band has been developed, but usually not to be used with molecular dynamics, but more as an optimization strategy in ab initio methods, right, in quantum chemistry methods. And so the first path metadynamics method was actually developed by Davide Branduardi, Francesco Gervasio, and Michele Parinello, and it was called From A to B in Free Energy Space, right? So we're building on that work as well. I will talk about these formulas later, but it's a way to project any point in this space on this path. So wherever I am in this space of collective variables, can I say where I am between A and B? If I call A 0 and B 1, where am I between 0 and 1? Am I here at 0.5 or 0.6? So I need some projection, and that's done with these formulas. So we'll talk about that as well. Of course, I should show you the alanine dipeptide example, otherwise no one believes me that this works. And that's what you see here. So the two things that we get out is an average path in the space of collective variables. So that's a little bit different than this initial method by Davide Branduardi and Gervasio and Parinello that I mentioned. Because in that case, although you can also use that now in the space of collective variables, but that initial paper talks about a path expressed in structures. So you have an initial structure, a reactant structure, you have a final structure, reactant and a product structure, and then you define a bunch of structures in between. And using an RMSD, you can sort of calculate where you are between all these different structures, and you can even optimize those structures to find a path. But here we really work with collective variables, and in the case of alanine dipeptide, there's two torsion angles, phi and psi, and we optimize that path. right? And that's what you see here. So these dots are the density sampled, and then so it finds this transition path here. And the second thing that we want to know is the free energy landscape. And in this case, the biasing method is metadynamics. I will talk a lot about metadynamics in this talk, although you could use other methods as well, like umbrella sampling, say, to optimize this free energy landscape along this path, right? So the bottleneck is somewhere here, which should then be this point here. Of course, this is minus the biasing potential, right? So the biasing potential is, of course, the opposite of this thing. But here's the reactance state already fixed to 0 free energy, so everything is relative to this this cross here, this point here. So I will also be talking about more recent extensions of the path metadynamics method, in particular the parallelization using multiple walkers. So we can have several simulations in parallel that sample parts of the path, and we can even have more paths. So here again we see this Ramachandran plot for the alanine dipeptide in vacuum, and if this is the product state, is the reactant state, then actually there's a crossing here. It's not so obvious that this is higher energy than here and here. And it would be nice to find all possible paths, right? And actually there's another path, because of course these torsion angles are periodic, so you could also exit here, so you rotate along psi. Then you would come back, well, if you go up here, you could come out here and then enter on this side. And so there's a high energy crossing on this side as well. So there's several paths, and with two of these paths, we can actually now find all paths and all free energy profiles along these different paths. So I'll talk about that in the second half. And a final note that I would like to make is that recently there's been a lot of work on finding collective variables, right? So, and even though with a path collective variable, the stress is a little bit less to find the perfect collective variables, because you can express them as a function, as a flexible function of these collective variables, but still you'd need as input good collective variables, of course. So how do you find those? What are good collective variables that describe your problem? And recent work has focused on data science methods, some machine learning methods, including us actually. And so I'll show you an example where you can use machine learning to find collective variables, and then use the path collective variable to see if that's a reasonable set, sample with those, get better data that you can feed to your machine learning, get better collective variables, and then in a couple of cycles, hopefully find good collective variables and find a free energy landscape. So that's if I have time, then the last time I will talk about. Of course, I should acknowledge some people. And in the last few years, most of the work that I will be talking about has been done by these three smart guys. This is Rakesh, Puttankalatil, Alberto. He implemented the multiple path and the multiple walker implementation. And Ambush, so yeah, the hydrogenase example that I showed is actually from Rakesh, and Ambush worked a lot on, both force field simulations using path collective variables, as well as DFT-MD work. And these are the two, these two papers I'll be talking mostly about, or I will show results from these two papers maybe. Okay, so that's the plan. I will talk about rare events, just to introduce you the problem again. Why are we interested in these methods, and why would you need them? In case you've never heard about these methods before, you probably would like to know about metadynamics, although I think I can probably be brief in this audience. And then, of course, I will talk about path metadynamics and about multiple paths, multiple walkers. At the end, I would like to say a little bit about this machine learning combination, and then I will talk about the exercise of this session. I sort of assumed that there's no questions so far, that this was still, no questions about the outline. But again, just a reminder, if anyone has a question, please don't hold still. So when we talk about rare events, of course, we mean rare events in simulations, right? So interestingly, in real life, in experiments, usually the things that we call rare events are not rare events. And the reason is that, well, in real life, timescales are a bit longer, seconds, hours, days. And of course, you have usually many more molecules, like 10 to the 20 molecules or so in a reaction, reactants. And so lots of stuff happening. And of course, in a simulation, you may have one protein that you simulate for a millisecond, or well, maybe a microsecond, let's say, and then well, depending on how high the barrier is, the rate will be extremely slow. So we do the opposite as in experiments. In experiments, you just see how much stuff is happening. So you measure the change in the concentration, and from that you measure the rate, and from the rate you can estimate the free energy change. And we do the opposite. We actually we have no idea about the rate. We try to calculate the free energy profile, and then from the height of the barrier we can estimate the rate and compare it to experiments or do predictions for experiments. So yeah. So what sort of processes are we talking about, and what sort of timescales are we talking about? Well, this is the fast stuff that we can sample without any problems. Nanoseconds, really no problems. But it starts here. All the cool stuff is happening here, the interesting things, and that will take a long time to see. And you may see it actually if you have a big computer and you simulate for long enough. But even if you see it a couple of times, right, then that still may not be good enough to have some statistics on the rate. No? So for example, an enzymatic reaction, you may see it if you sample a microsecond. Of course, you're wasting a lot of computer time, waiting, and then at some point something happens. But even then, you would like to usually have some statistics and sample many crossings, and so we need better methods. So these methods can be, as I mentioned, ab initio, molecular dynamics, DFT-MD, we use a lot, or force fields, MD simulations, but also coarse-grained simulations or QMM, etc. Right? And I'll be talking about this off-diagonal part here, the so-called rare event methods. Right? So we want to use all these sampling methods and enhance them along this axis, the timescale axis. Right. Now. The thing is that, yeah, as I said, transitions, molecular transitions, such as phase transitions and self-assembly and chemical reactions and such are rare events, and so often we need a good reaction coordinate to describe this, and so for example, for this sort of reaction, a so-called SN2 reaction, I'll show you an explicit example in a minute, where A reacts with BC and forms new molecule AB, and C goes off. We can easily think of what are good collective variables. Maybe this distance here, AB, the distance AB here on the x-axis, and then the distance BC of the leaving group here, and then the underlying energy profile or free energy profile may look like something like this, with a reactant state here and a product state here, or the other way around. And we can think of some sort of minimum free energy path that crosses some bottleneck somewhere here, right? So this will be the transition state in this somewhat symmetrical landscape, and this is what it would look like in 3D. So that's why you will always hear me talk about reaction channels. So this is because I look at it as a channel. Some people would say, but it's a pass, right? Like if you're used to mountains, then you would call this a pass. But what do I know about mountains? I'm Dutch, so I will call this a channel. In Amsterdam, we have a lot of channels, so this is a channel to me. But you already see the problem here. So if we want to talk about a good reaction coordinate in a space of two collective variables, it's some curved thing, and it may not be so easy, right, to really find and define with a curve this minimum free energy path, or average reaction path, say. And yeah, so I'll show you some more examples in a second of this sort of problems. Yeah, to sample these rare events, the community has really developed a plethora of methods, right? So there's a long list of methods, and what you see here is by far not complete. And here I group them in 4 types of enhanced sampling methods. Maybe I'll start in this corner here. So the simplest thing that you could do to enhance the sampling of barrier crossing is just raise the temperature, right? So if you make stuff hotter, you put more energy in the system, and it may actually go over the barrier. And then there's fancy versions of that, so replica exchange or parallel tempering, where you actually mix low temperature and high temperature in parallel, and adiabatic molecular dynamics, etc., where you just increase the kinetic energy only for part of the system, right? That's one way of doing it. There's also methods where you, for example, constrain along some reaction coordinate. So let's say you know a reaction coordinate or a collective variable, and you constrain it. So either you fix it completely, and then you integrate along the mean force of constraint to get a free energy profile, or you just pull it. You pull it out of equilibrium, right? And so there's these methods that I call thermodynamic integration. And then on top here we have methods that really focus on finding a path, reaction path. And I already mentioned the string method by Erik van den Einde and co-workers. But of course there's also methods that don't really bias anything, such as transition path sampling. You only need to know the initial states, and then you can generate paths and equilibrate reaction paths that go from A to B, and sample a so-called path ensemble, right? And then there's more fancy versions where you put interfaces, so you can actually try to estimate a free energy landscape as well. So this is sort of interesting. It already focuses on the reaction path, right, which is exactly what we're after. And then maybe the last group that I want to talk about is where we add a bias potential. So it looks a little bit like this one. We have a reaction coordinate, but instead of constraining it or just pulling it, we will add a biasing potential. Umbrella sampling is maybe the most famous one, and most used one, I would say. In fact, it's probably my favorite method, because it's very robust. It's very clear what you're doing. You're adding a bunch of windows. You measure a histogram on the part that you can sample in that window, and then you glue the log of the histograms together using some reweighting, for example, the WAM method, and you'll have a free energy profile. And these are all methods that are related to that. For example, metadynamics. I'll be talking a lot about metadynamics, of course, where you just bias adaptively. So path metadynamics combines actually ideas from the top 2, right? So we'll define a path. We have to optimize that path, like using methods similar to string method, but we want to bias along that path using this sort of enhanced sampling methods, so metadynamics or umbrella sampling or these sort of methods. So that's where event sampling and all sorts of methods that we can use for that. I'm going to focus now on metadynamics, and then after that on path metadynamics. So first, what is metadynamics? So metadynamics is already a 20-year-old idea. In fact, after the summer, we're going to celebrate 20 years of escaping free energy minima, the metadynamics method, in a nice CCAM workshop called 20 Years of Metadynamics. And the method was, as you probably all well know, introduced by Alessandro Laio and Michele Parinello. And the idea was very simple. You just add a time-dependent potential to your Hamiltonian that is built up of Gaussian kernels, right? So here you recognize the Gaussian that work on some collective variables S that you push to every time T star, T prime, and so you build up a biasing potential. Right, so this is a sum over time from the past until now, time t, of these Gaussians that have some width and some height h, and the fact that there's a product here means that they are multivariate Gaussians, which means you can have more than one collective variable. So alpha is the product over collective variables, right? So for example, 2, you could have S1 and S2. So 2 collective variables or more, right? So that's really nice. You can use it for enhanced sampling and probing the free energy landscape, because if you do this carefully enough, then this biasing potential will actually be an estimator of the underlying free energy landscape in the space of these collective variables alpha. And so the cool thing at the time when this was introduced is that you can really use it for multiple collective variables, and most methods at that time were used for just a single collective variable. Although there was a two-dimensional umbrella sampling was sometimes used, but it was painful, and this had a much better prefactor, let's say. So I dug up this movie again from an ancient past for this masterclass, and here it goes. This is my Dutch view. What you do with mountains, where you have to go from one minima to another minima over transition states. You change the landscape by flooding, and that's what's happening here. So your biasing potential follows your dynamics, this little guy, until everything's flat, and then you just have a diffusive dynamics, and you don't feel any mountains anymore, right? So that's the idea. At least that's how I look at it. And so here's one of my first examples. Oh, I already see a chat. Okay, that's that's Max. Thanks, man. Thanks, Max. So this was one of my first tryouts actually on this system, and this is again the SN2 reaction that I showed you already in the beginning, but now here with real atoms and molecules. So here's the reactant state. This is the product state, and this is this is the transition state, and this is the product state. And so the leaving group and the attacking group are the same. So this thing is perfectly symmetric. And so of course we know good collective variables of this. You could use this distance here and this distance here between the carbon and the chlorine. So we have two distances, and you can bias them with metadynamics. So initially, as a function of the number of Gaussians, in those days I called them hills actually, placed. So time is expressed here in the number of Gaussians. So here we have added 500 Gaussians to our biasing potential in metadynamics, 1000, 1500, 2000 Gaussians. And adding more and more Gaussians, then here we see a recrossing. So initially one distance is short, right? This distance is short, the other distance is long, making larger fluctuations. And then at some point here it crosses after about 500 Gaussians. And then now we are in the product state. Now notice that this time takes much longer to fill. This takes about 100 Gaussians. Instead, this one takes only 500 Gaussians. And the reason was that I made the Gaussians smaller, right? So because it's symmetric, it should be the same. And you can actually see that in the buildup of the free energy landscape. So this is now minus the biasing potential. And here I used larger Gaussians, and so the thing is a bit rough. And then you see it crossing at some point. So there it goes. And actually now it goes much slower, the buildup, and more smooth. And this was when the method was just introduced, and we were still trying to figure out how it works and how to choose the parameters. How high should the Gaussians be, and how wide, and how often should you drop them, right? So this was one of my first experiences with metadynamics. But the cool thing was that clearly we don't need to know anymore the perfect reaction coordinates. So we don't need to know what is a good reaction coordinate. All we need to know is good collective variables, and then it will find some sort of path. And already from this picture, it's also clear that the thing we should be after is actually the lowest free energy path, right? So it would be nice to know what is the lowest free energy path. And if you want to know how high is the barrier, then you should actually integrate over this well in the orthogonal direction. To find the highest point here with respect to all this space here in the reactant state or the product state. This is another example that I just want to flash by at you for 1 second, because now things start to be complicated, and I was curious, how far can we push this method? How far can we go with this metadynamics? So that was the SN2 reaction, right? Chapter 1 of your organic chemistry book, and this is then probably chapter 2, the E2 reaction. And the point is that for the E2 reaction, where now we have, again, an attacking group that grabs here a hydrogen, and then on the other side, there's a leaving group going, and you end up with ethylene and HF and F minus if you have fluorides here as the attacking group and the leaving group. And here the point is that this is a spectrum of possible transition states, and so now it's really complicated to come up with a good reaction coordinate, because we don't know in advance what the transition state looks like. So if you have a good leaving group, then maybe this is a transition state where the leaving group goes, and after that, the attacking group goes away with this proton. Or it goes perfectly concerted. Or maybe first the proton is going, and then after the proton is completely gone, the fluorine will go. So that could be the spectrum of possible transition states. And then there's a competition with SN2 reactions, because the fluorine can grab this proton here, but it could also do an SN2 reaction here, actually. So it could replace this fluorine on the carbon. So, and that's what we try to sample with 6 collective variables. I'm not sure if people have tried more collective variables with metadynamics. Maybe Max knows, but I like to believe it's still the record today, 6 collective variables with metadynamics. And they're all coordination numbers. So CN stands for coordination numbers. So the number of carbons around the fluorine. So there's 2 fluorines, right? So we have a black line and a red line, which are the 2 different coordination numbers around the fluorines. The number of hydrogens around fluorines, which is, well, it's 1 here, right? And it's 0 there. And then the number of hydrogens around carbon. So in this case, this one has 2, but in this case it has 3. So it varies from 2 to 3. And again, there's 2 carbons, so we have 2 of these coordination numbers. So 6 collective variables. And I put more than 10,000 Gaussians in this simulation. And we can then recognize several reactant and product states, right? Now, there's of course a lot of symmetry, right? Because if you exchange 2 fluorines, or if you exchange the 2 carbons, then you have again the same species. So the total number of stable states in this free energy landscape is 8, actually. So we have 8. Each one here is a reactant or a product state, just exchanging fluorines, right? And so you have a hydrogen exchange, or an SN2 reaction, or an E2 reaction, etc. And yeah, we managed to sample all of those, but of course there was no hope to converge the free energy landscape. It was too complicated. In 6 dimensions with metadynamics, you can only hope to escape the minima and hop from one to the other with big Gaussians. But at least in those days we could not converge the landscape. But we did manage to then find these minimum free energy paths, right? So you see already where I'm going here. We decided, let's go after these free energy pathways. And so here's the reactant state, and we can either do an SN2 reaction. So here we have the SN2 product, or if you follow the red lines, this is again another free energy path. We get the E2 reaction, right? And so where these 2 white surfaces touch is a transition state for this reaction. And where the 2 yellow surfaces touch here is the transition state for the SN2 reaction. So that was a nice success, but we realized that also metadynamics has its limits, and 6 collective variables is not really doable. Instead, what we did then was focus on these red lines. So first use metadynamics to find the transitions and find the transition paths, and then switch to a 1D sampling along the path. So we would find this path and then describe it, put a string of nodes in there and then sample along that path and converge the free energy landscape in one dimension for first for this path and then for the other one. So,
sorry, Professor, one question.
Yes. Yes, please.
Yeah. Well, just about when you say that you biased 6 collective variables, my question is, you biased them together in the same simulation or independent simulations biased independently?
No, they were. What do you mean? So they're not independently, right? So they can all move. So there's really 6 independent collective variables. Or maybe I misunderstand your question.
For instance, in order to bias the first collective variable, you performed one simulation and you didn't care at all about the other collective variables, but you only biased the other ones and the only one, and the other one, and the rest was just monitor.
Right.
So it was one biased collective variable only then.
Yeah, but no, that's not the case. No, that's not the way to look at it. And it is a good question, actually, because it's a bit abstract, of course, to understand. So how does this biasing work exactly? And so, okay, first I show you again the formula, and then, no, I want to go back. Can I not go back? Hey. Sorry about that. We have to watch the whole movie. No. So this formula I want to show. So the point is that this biasing potential is, as I said, a product, a sum of Gaussians, and these Gaussians are multidimensional, right? So it's like, suppose that I'm in 2 dimensions, right? So like I have a landscape of 2 dimensions of 2 collective variables, for example. And the Gaussian that I put is then a 2-dimensional Gaussian. So it's really like a 2-dimensional bump in the X direction and Y direction, for example. And that means that I push collective variables in the X direction, but another collective variable in the Y direction, I also push simultaneously. And let's see if that's more clear in this example. So in this case, the free energy landscape has 2 collective variables. There's 2 distances, this distance here and this distance there. And so I have here on the X and Y axis the 2 distances. And what you see here is a Gaussian, but many Gaussians, a sum of Gaussians, but upside down. So I already show here the free energy landscape. But of course, if we make minus this landscape, so then they look they are positive instead of negative. That's the real biasing potential, the metadynamics biasing potential. And so if I put one somewhere in this landscape, let's say in the middle, I put a little bump, it's a 2-dimensional bump, then the system can either decide to move away from that bump in the direction of this distance, or the direction of that distance, or maybe both, right? It's pushing both distances, both collective variables. So I'm biasing both at the same time. And the system decides which one it wants to move. And so, for example, when I'm here in this minimum here, one distance is very long, which is this distance from the chlorine to the carbon. It's a long distance. There is no bond here, and the chlorine can easily move back and forth. And that's what you see here. There's a large motion, and it's also what you see here. So the motion is large fluctuations. Instead, the other one is short distance here, because it's covalently bonded, and so the fluctuations in this direction along this axis here, they're small, right? So if I put a Gaussian here, I'm biasing both collective variables at the same time, but it's much easier to move along this axis, along this distance, because that one's not bound, and it's much easier to move the chlorine further away or closer by than it is to break this bond, for example. So this bond is now short. This is in atomic units. So it's about 3 atomic units. So that's 1.5 angstrom, and it doesn't want to become shorter or longer, right? So I first have to fill it, and then I can cross at some point, and then here the opposite is happening, and I can move easily this distance and not so much that one, because it's bound, right? So And that's, of course, also happening in this example here, except that I cannot visualize it very well because it's an 8-dimensional problem instead of 2, and I don't know how to show you an 8-dimensional landscape. So I can only show you projections. And so this is a projection of only 3. So I just chose 3 collective variables out of the 8, right? So it's 2 here, black and red, two more here, and 2 more here. Sorry, 6. There's 6 collective variables. I'm sorry, 6-dimensional space. And I just chose 3 of them. So one of these 2, one of these 2, and one of these 2. And that's what you see here on the 3 axes. And this is a 3-dimensional landscape. And if I'm in this state here, right, so I'm in this reactant state, and I put here a 3-dimensional Gaussian, then all 6 collective variables are biased. And that's what you see here. So, you know, one collective variable has a short one, the other one is large, and start to fluctuate, etc. And the system decides what's happening first. Am I first moving in this direction or first in that direction? Does that answer your question a bit?
Completely, Professor. Thank you very much.
Okay, well, thanks for the question. I'm happy that things are clear. So at the same time, while we were working on this sort of problems, trying to understand how accurate these methods are and how does it scale with the number of collective variables and things like this, Alessandro wrote a very nice paper with coworkers and in the group of Parinello called "Assessing the Accuracy of Metadynamics." And that was very nice work. There's no molecules involved here. It's just an analytic potential using a Langevin dynamics. And it's very nice to work with that sort of systems. It's a bit abstract, of course, but they're very quick and you can converge them very easily. And so, in fact, also in the exercises, we'll use this approach. And the nice thing is that they could really come up with see how the error in the estimation of the free energy landscape scales with the parameters of the system. And actually these parameters, these H, W, S, tau, D, and beta that you see here, 3 of them are parameters that you have to set for metadynamics, and 3 of them are parameters in your molecular system, right? So the first 3 are metadynamics parameters. So how high are these Gaussians that you put every time? How often do you put them? And what's the width of them, right? So that's 3 parameters that determine the error. So if you make the Gaussians very high or very wide, or if you put them very often, then the error goes up with the square root of the height and the width. So it's good to know, because you would think, well, let's put very big Gaussians, so I fill quickly and then I'm quickly to the product state. So I sample fast, and in fact, that's what we did in this 6-dimensional problem that I showed you. But then the error will be large. And then the other 3 are system system parameters. So, for example, how large is this free energy landscape that you have to sample? If it's very large, then your error may go up. And also, the diffusion coefficient and the temperature are important parameters. So if the diffusivity of the system is slow, then the error may go up, unless you then also adapt how often you put the Gaussians, right? So this is very nice because it tells you how to parameterize metadynamics. Okay, so we at the same time we wrote this paper called "A Recipe for the Computation of the Free Energy Barrier and Lowest Free Energy Path of Concerted Reactions," and we looked at pitfalls. So how do you parameterize this, and how do you so in practice for real molecular systems? And actually it matches very well this paper of Lyo and co-workers. And as I said, we start with doing a simulation in several dimensions. Then, for example, in this case, in 2 dimensionals with 2 collective variables, we find this minimum free energy path, and then we use this path to sample in 1D, where now we go from 0 to 1, for example, or in this case from 0.2 to 0.8, and converge nicely the free energy landscape in one dimension, which is much faster. I will skip this, but so it's always nice to find out what to look at to see if your dynamics and your method behaves in the way it should look like. And so we recognize that there are several things that can go wrong with metadynamics. And yeah, I can talk about that more. So for example, I always like to see that so if you look at the dynamics of the collective variables as a function of time, that you should see slowly increasingly larger and larger fluctuations until you escape. And the reason is that, yeah, you're in this minimum, this free energy minima, and so you have small fluctuations in your collective variable. But then when you go higher in energy, you should be able to make larger and larger fluctuations. And if you see instead of very crooked dynamics, yeah, that's suspicious, and you'll probably have large errors in your free energy. There's other problems, and yeah, I can talk about that if you have questions later on, or otherwise I recommend you to that paper called A Recipe. Of course, the slides will become online and I can also post it in Slack actually if you're interested. Now, I cannot even see my own slide. Yeah, so one problem is, of course, yeah, how do we know if we have all the collective variables that we need? And that's very important, even for path metadynamics. And so I like to always show this little example where we have, for example, sodium and chlorine, right? And everyone would immediately say, well, if you're interested in the solvation of sodium and chlorine, so we start with them bonded, we put them in water, and we are interested in the dissociation, then the distance should be a good collective variable. And then the problem is that, yeah, if you use a biasing method to calculate the free energy landscape, for example, you push them slowly apart, you may find a free energy profile where it looks like it's going up, it's going uphill, this black profile. And the reason is that you did not take into account the reorganization of the solvation. So the chlorine needs to be nicely solvated, the sodium needs to be solvated, and that may be a slow process, right? So that could be a hidden collective variable, and if you miss out on that hidden collective variable, then you'll find the wrong profile, and if you take that into account, then you find actually a much better profile. And one thing that is often easy to check is whether or not you have hysteresis. So if you now look at the reverse process and you bring them closer together, and you find then a profile where suddenly, first on the way there you find the black profile, you think, well, that looks fine. And then you go back and you find a profile where now suddenly it's the other way around, so it goes uphill the other way. That's of course highly suspicious. So if you go forward or backward, you should get the same profile. And if that's not the case, then probably you're missing out on collective variables, important collective variables. Okay, I will skip this one. And I will also skip advances of metadynamics. Of course, well-tempered metadynamics is a really nice method by Alessandro Barducci, Giovanni Bussi, and Michele Parinello that takes care of the convergence. And I invite you very much to try this in the exercises with path metadynamics as well. So you can use plain metadynamics to fill up a profile along a path. But of course, you can also use the well-tempered metadynamics. And then the convergence is guaranteed, so to say. Right? It's a bit more tricky, the interpretation, and I'm more than happy to talk about that as well if you have questions about that. Another nice thing is multiple walkers. So this was implemented by Paolo Raitiri, if I'm not mistaken, for metadynamics, and we have a version for path metadynamics as well. And basically, it's just a parallelization where you have simulations in parallel. So instead of having one walker that is being biased, you have now several, and you can also start them in different minima, and they all have their own biasing potential that biases them, and they talk to each other about my biasing potential here looks like this, and mine looks like that, and so they exchange information, which is a trivial scaling of because it's so little information. And then, of course, the sampling is much faster. So that's a very nice idea. Multiple walker metadynamics. Okay, so all you need to know about metadynamics, and now I want to move on with path metadynamics because, well, as I said, it's a beautiful method to learn the free energy landscape on the fly, but it actually scales only well up to, let's say, 2 or 3 collective variables. And if you need more collective variables, it starts to become painful, and it would be better to just immediately focus on the minimum free energy path. And that's what we try to do with path metadynamics. So how does it work? We add one extra collective variable. I call it sigma here. And sigma is a function of all the other collective variables. And basically, sigma is doing all the work for all the collective variables, because the biasing potential that we're building up with metadynamics, or if we use another biasing method like umbrella sampling or steered MD or constrained MD or adaptive force bias, then the bias is only on this sigma, and sigma passes it on the other collective variables. So in other words, sigma is just a function of all the other collective variables. So, and the collective variables, of course, are functions of the atom positions, right? So this could be distances or angles or dihedral angles or all sorts of collective variables that are functions of the atomic positions. And then the path collective variable, sigma, is just a function of those collective variables. So we have one extra layer. So then now the whole thing is one-dimensional again, because this is a one-dimensional function. And so now we do one-dimensional metadynamics. But the point is, the question is, what is that function? Right? So now we have to also figure out what is the function in the space of these collective variables. And the way we pose that question is, we see the function as a path in the space of collective variable. And so we have to adapt, we have to learn that path. So how do we do that? Well, let me first tell you a little bit about paths in space and so-called committer probabilities. Maybe you've heard about committer probabilities. So you can imagine that we have a trajectory from A to B, right? Suppose we were lucky, we simulated for a long time, at some point it escaped and it went to B. Now, if you just look at your movie, where first it's in A and then it's in B, you can ask yourself, where was the transition state of this trajectory? Did it pass the transition state? Of course, you can look at the total energy or the potential energy, but usually the potential energy doesn't tell you so much, especially if your system is a bit big and maybe you have solvent. Then it's dominated by thermal energies or of all these other degrees of freedom that are not so important. And you should have known what is the free energy landscape along that some collective variable. But let's say we don't have that. Can we still say something about transition state? And the answer is yes. Because what you can do is you can pick a point, choose a frame of your movie, of your trajectory, and launch simulations from that movie with from that frame, from that configuration, somewhere halfway between A and B, with random velocities drawn from a Boltzmann distribution of that temperature that you were doing. Now, if you're close to B, then probably most of the trajectories will go to B, and maybe none or only few go to A. And if you do that close to A, probably all of them will go to A. And we can look at the probability. If we launch enough, maybe 100 or 1000, then in principle you can calculate that probability to fall in B arbitrarily accurately. So if we're close to B, probability will be close to 1 because all trajectories would go to B, and if we're close to A, then this probability will be close to 0, and maybe none of them will go to B. But of course, somewhere in the middle, there must be a frame, a configuration where half of them will go to B and half will go to A. So the committed probability to go to B is a half, and this we can define as the transition state. This should be the transition state, right? And so we don't know anything about the free energy landscape, or we don't need to know anything about the underlying free energy. We don't need to know if it's a saddle point, right? We don't need to know if it comes from all sorts of kinetic factors on top of free energy landscape. This is really including everything. We just look at the probability if we launch a lot of trajectories. Now, of course, there's not one point. There could be many paths that go from A to B. Maybe there's an infinite number of trajectories that can go from A to B. And each of them, of course, must pass through a point where the committed probability would be a half. I mean, it's painful to calculate. You may have to launch hundreds of simulations. But in principle, we know it exists, right? we know that each trajectory should have a point with committed probability a half. Now we can say, well, then there must be a hyperplane in some space here with which has all these configurations with probability, committed probability a half, right? In fact, there should be a continuous foliation of many, infinite number of hyperplanes with probabilities that go from 0 to, a half to, 0.6, 0.7, 0.99, 1, right? So we can divide the space up into, all configurations that fall in one of these hyperplanes, the so-called isocommitter surfaces that have the same probability if you're in that plane to fall into B if you would launch a lot of trajectories from that. So this is an interesting concept because now we can ask ourselves, well, if we have these hyperplanes and we would launch, many trajectories, and we can actually look in each plane, where do we cross, right? So where is the maximum flux in all of those hyperplanes, and so where is the where's the maximum flux? If we connect all the points in all these planes, we will get, of course, the average transition pathway. And again, I have not said anything about free energy landscapes, right? So, probably this average transition pathway is the same or is very close to the minimum free energy path, but it doesn't have to be, right? Only if you would have a symmetric channel, it could be, but it doesn't have to be. But it's probably close to the minimum free energy pathway. Now the question is, how do we find this average transition pathway? Because as I said, calculating these isocommitter surfaces is painfully expensive, and then we would have to calculate these fluxes, etc. Can we find this pathway in another way? And the idea is as follows. Let's start with a guess path. So I just define some path that goes from A to B with a bunch of nodes. And all I do is that if I am able to bias the dynamics along my guess path, maybe I use metadynamics or some other method, then I can see, do I on average orthogonally to this path spend my time on average on that path, or am I a little bit on the left or the right or the top or the bottom in some space? Now, what is this space? This must be a space of collective variables, right? I should be able to define this space in collective variables. Maybe there's a collective variable in this direction and a collective variable in that direction, or it could also be higher dimensional. And in this space of collective variables, I can see, am I on the left or am I on average on each node? And I can do that everywhere along this path. I can keep track of, what is the average distance of points sampled here to the node. And then all I need to know is if that distance on average is not 0, I just move my nodes there. And I can do that all the time, right? I can all the time measure the average distance, and I can keep on measuring and converge that until all the distances to the average flux is 0. And then I found my average transition path. So here's this very simple algorithm, again explained in a space of two collective variables. There's a minimum here, there's a minimum there. So these are my two collective variables. I have some guess path. I bias, along my path to move from the reactor state to the product state. But maybe on the average, I spend my time on the left or on the right. So for example, I'm at some point during my simulation, I'm here, and I can calculate the distance to my nodes. And then I can say, oh, I should move my nodes to this direction on average, depending on how many samples do I have on the left and on the right of this path. So that's the idea. Now to do that, I need some way to calculate that distance. And that means that for each point here, I should be able to calculate the closest point on my path and then calculate that distance. And that gives me a so-called foliation of projections onto my path in this collective variable space. So that's what you see here. And in fact, this is an example of a foliation. This is from an alanine dipeptide Ramachandran plot. So these are, again, the usual phi and psi angles, right? This is the product state, this is the reactant state, and this is now a path, a possible path. This could be the minimum free energy path, but it doesn't matter. Let's say some path. And what you see here, this space, all these little lines, are, all the planes, I was going to say, but of course in 2D they're just lines that have the same value. So here, this line, this dotted line, has the value 0, right? So here I'm at 0, and if I move in this direction, I move to 1. In fact, this dotted line is 1. And so this gives a foliation. So if I'm somewhere here, then my value is 0.6 because I'm able to project it here. So how do I calculate this projection? I'm going to skip it, but I'm using this formula, and if you want, I can explain that formula. It's also published in a paper by Linus and myself, and I can also point you there. But it's a pretty simple idea. The idea is that if you have a space of collective variables, so this is supposed to look like a 3-dimensional space, and there's a path of nodes going through here. So these black things are nodes. Could be a higher dimensional space, doesn't matter. But let's say there's 3-dimensional space and there's nodes here. Then if I'm at some point in this space, for example, I'm at this point Z here, I can always try to find the closest node number I, right? That's this, I min, the minimum, the closest node. And if I have M nodes, then, and this is node number small m, then I already know that I am between, close to m, the number of my node divided by the total number of nodes. I'm somewhere close to this number, right? And I'm probably a little bit on the left or on the right. So what I do is I find the closest node and the node before and the node after. So this is the closest node, the second closest node, and the third closest node, right? And I can calculate the distances to all these nodes. And then all I need to know is, where am I between the closest node and the second closest node? Am I, halfway or what? And the idea is that if you have 3 nodes, these 3 closest nodes, you can always draw a circle through these nodes, no matter the dimensionality of the space. So you have to draw this circle, which has the center. So in higher dimensions, it becomes a bit more tricky, but it's with the circle, with the center closest to these 3 nodes, right? And then what we do is we would like to know where we are on this arc, the arc that goes through this dotted line, part of the circle that goes through these 3 nodes. Oh, excuse me. Now, that's not exactly what we calculate. So I would like to know, where am I on this thing, which is basically drawn by this plane here, this gray plane. But instead of calculating that point, actually what I'm calculating is instead the projection on that line here. So there's a projection here. And that's this thing, this simple formula. It's just a quadratic formula, pretty simple actually. Well, I mean, maybe it looks complicated, but the derivation is rather trivial. Anyone can do it, so I can point you to it actually. I'm going to skip it for now, but so that's all there is to it. So yeah, the idea is that in principle you can draw a circle. Then in practice we don't do that. We have to calculate this estimate. And what is the case is that this point here, this ratio, the point of, well, let's say this distance with respect to the total distance between these 2 nodes is the same as another point x here, which has this ratio of this to that. And what is special about this point x? What is special about this point x is that the distance from this point x to where I am is the same as that to the second closest node. So this length is the same as that length. So if I'm exactly closest here, then these 2 distances, well, okay, no, now it becomes too complicated. I can go into this. But anyway, so that's all there is to it. I just calculate where is this point x, which is the ratio of this length, this length, which is given by this formula. And that gives us a very nice and easy projection. There can be somewhat problems if the curvature is too high, which means I have too many nodes and I make too sharp turns, and that happens here, right? So what could happen is that if I pass through here, so I'm very far away from my transition path, and I pass through here, let's say, I can suddenly jump from the value of 0.9 to 0.1, for example. Instead of first passing through, 0.8, 7, 6, 5, 4, 3, 2, 1, I should pass through here. But see how here all the lines, the ISO lines fall together, and that could give problems. And if you want, I can also go into that. If you have questions about that, I'm more happy to discuss that and what you can do about it. Okay, so that's how we project any point in collective variable space onto a path using this simple formula. And we have a second formula to calculate actually also the distance to the path, which is called z. So usually we call this sigma or s. So where we are between 0 and 1. And then we have z, which is a measure of where we are, how far we are away from the path. So here again, alanine peptide. I think I can go over this one pretty quickly, but this shows you how we use path metadynamics to start from a straight line. And then while we sample, we move those nodes to the density that we have sampled, the green spots. At the same time here, we're building up the biasing potential of the metadynamics, which is now a one-dimensional biasing potential between 0 and 1. 0 is a point here, and 1 is a point there. Maybe I show one more time. So we're starting, so these, we have a string of nodes. The total number of nodes is 20 plus 20 plus 20. So we have two fixed nodes. The minimum here is fixed, and this one here is fixed, and there are 20 nodes in between. Then we also put so-called trailing nodes. So there's 20 nodes there and 20 nodes there. You don't need them, but sometimes it's nice to see that, you know, if you go smaller than 0 or larger than 1, frequency goes up again as well, right? So we have a minimum, and it doesn't just stop here, but we also like to know what's happening here. And so it's sometimes nice to have some trailing nodes. We put small Gaussians. This is in kelvins, so, you know, pretty small, and some width. It doesn't matter the units. You can also use kilocalories or kilojoules, of course. And every 100 MD steps, we put a Gaussian. And then every 100 MD steps, we move the nodes, right? So a little bit less often than we put Gaussians actually in this example. And every recrossing, so every time we cross and we cross back, what we do is to converge is we make the height smaller and the width as well, and we increase this update time by 100 here. And so that's how we converge. Although actually this movie only shows you the first crossing and the first recrossing. But then in practice what we do is we continue until we have a smooth curve here, a smooth path, and a smooth free energy landscape. And so in a single simulation, we get the reaction path and we get the free energy profile. Okay, so that's path metadynamics. And now a little bit about the latest. I'm already way over time, actually, I see. Yeah, I guess I talked too much. But I still want to show you a little bit about the latest advances where we look at the multiple paths. And this is work done by Alberto, who moved on now. Last year he graduated, and now he's in Utrecht, actually, as a postdoctoral fellow. But he did really nice work with some longer peptides. So we started with alanine dipeptide, but now this is polyproline oligomers. And the nice thing is you can make them longer and longer. And so we can use more and more collective variables and see how that scales. So this is a tetramer. So we have a tetramer of polyproline, and it rotates around the omega angle from 0 to 180, and we go from a right-handed helix to a left-handed helix. And so if we have a tetramer, so 1, 2, 3, 4 prolines, we actually have 3 omega angles. So we use 3 collective variables, but then we can also go to 4, 5, 6, etc. So this is again the metadynamic settings, and I can show you, yeah. So this is the tetramer. We have 3 omega angles, omega 1, omega 2, and omega 3. And again, we start from a simple straight line as the guess path. And then when we start biasing, you see that the path quickly optimizes to a stepwise path, right? So it's not a concerted change. What you see is actually that it will first move along omega 1. So first we go in this direction, you know, one torsion angle rotates, then the next rotates, omega 3 in this case, and then we go down here, which is, it's just omega 3 times 2 times. This should be omega 2 then, I guess, and this is omega 3, we go down, and we arrive in the product state. So these different colors here is an implementation of Alberto using multiple walkers. So actually he started here with 8 simultaneous simulations, and they all, so 4 started in the product state, 4 started in the reactor state. Let me show you the movie one more time. The different colors going, and then quickly, you know, once the path is found, they can go back and forth, and this simulation takes about 10 nanoseconds, and then we have a converged profile. Actually, this is the free energy profile, and you see each torsion angle rotation has a little barrier, and it follows the so-called zipper mechanism. It's what they call it. So first number 1, then number 2, number 3. So yeah, the zipper-like mechanism, and this is in agreement with what is seen experimentally. Now, interestingly, you can. I mean, the order can change, right? It could also have done first number 3, then number 2, and then number 1, right? And actually, there is in this case 6 different pathways, right? So 3 factorial pathways. If we have 3 collective variables, then there's 3 factorial ways of ordering this. And so there are actually 6 possible pathways, and we would like to find all of them. Oh, this is just a quick slide, intermediate slide, to show you how the scaling goes if we go to more collective variables. So this is the tetramer with 3 collective variables, which I just showed, and this, if we make the peptide a little bit longer, we have 4 collective variables. This is 5 collective variables, and what we see is actually that the scaling. So this is now the convergence of the path measured in the RMSD with respect to the initial path is pretty quick, right? And it's actually sublinear. And this is the free energy surface convergence is also very, very quick, actually. Right. So if you would use normal metadynamics, you would have an exponential scaling, but but with path metadynamics, the scaling is even faster than linear, which is quite nice. But the number of paths grows factorially, as I said, with the number of collective variables, and it would be nice to find all of them. And so I started talking about, single walkers, so normal path metadynamics, where you have a path and you sample this path and you optimize this path. And I just showed you with polyproline that we now have a multiple walker implementation. So we have several simulations in parallel, and they talk to each other about moving the path and optimizing the biasing potential. And then the third thing that I want to show you is that we can even do several paths that have their own walkers. But then the problem is, how do you make sure that if they all start from a linear interpolation, the same guess path, that they not fall all in the same reaction channel? And the way this is solved by Alberto is he used so-called repellers. And what are repellers? Repeller is a simulation that just sits there in some potential. And what is this potential? This potential is this walker samples this path in principle, and then I have another walker here that I also designate repeller, and they repel each other. So if this one falls in one reaction channel, it pushes away this walker, and this walker is on this path and will bring this path with it. And so that way you can actually move paths away from each other, and they fall in different reaction channels. And that's what you see here. Again, for alanine dipeptide, there's 2 lines here, both on top of each other, of a gas path. And so we have 3 walkers per path, so 6 walkers. And then we have also 1 walker per path. So in total we have 8 simulations in parallel. 2 of them are repelling each other and just moving the paths away from each other. And these repellers, we first move them to sigma, or S is a half, so they sit somewhere here in halfway, and they cannot move back to the left or to the right, so they have to stay around 1/2. They don't help in the sampling of the path or in the sampling of the free energy landscape. That's done by the other walkers. All they do is make sure that the 2 paths repel each other. And that's what you see here. So the purple one and the green one are the repellers, and you see they don't move. And the other guys, they optimize the path and they optimize the free energy landscape. And here you see the free energy along the 2 pathways. So here is a crossing, and here's a crossing, and maybe it's not so clear, but this is a little bit higher in free energy. And so we can actually go to more complex systems. This is again the polyproline example where there are 6 paths, and so we have repellers here and here, and they repel each other, and so we find again all the possible paths, which is really nice because now we can find all possible reaction pathways and free energy profiles. This is implemented and also made available on PLUMED Nest. Maybe you've heard about this, PLUMED Nest. It's very nice. If you look on the PLUMED website, there's this so-called PLUMED Nest, and it has so-called PLUMED eggs in the PLUMED Nest, and each egg is an example of a type of simulation. And so Alberto, he made an example with input files and output files of this path collector variable with metadynamics and the multiple walkers for polyproline, and you can just download it, right? So you just look up. So if you search, the easiest way is to search for Alberto's last name, or you just, well, you use this number, but then you have to know the ID of the egg, number 33. And then you can download it and you can run your own example and adapt it to your own problem. And there's the link to the paper, of course. This I skip for now. And we're now here. Maybe I also skip this part because I just want to talk a little bit about the exercises, and then maybe I can stop around 5:30. And I think 1.5 hours is long enough. Difficult to concentrate so long. Are there any questions until here? Or are there people that really want me to talk about machine learning? Then you can also speak up now. Then I will still. Is it okay if I continue with going a little bit about the exercises? It will take me 5 or 10 minutes, and then I will conclude. I think you're already sleeping, aren't you? I see something in the chat. Sure. Okay. Okay and sure. So that I think that's okay and sure for my plan to skip for now the machine learning. As I said, the slides will become available, and if you have questions about it, ask me in the Slack. But then now I can continue with the exercises. Okay. Yeah. So maybe just to answer a few questions that may also things that you will have to worry about in the exercises. How to do this in practice. So this slide is, I call it a recipe for using a path collector variable. So what do you need to do? So if you want to do path collector variables, you first need to know the stable states, because you're going to define a path between the stable states, right? And the way to do that usually is, just run an equilibrium simulation in both states, in A and in B, and make sure that they stay there, so they're really stable states. And then if you choose the collector variables to describe your transition to go from A to B, which can be distances or angles or all sorts of collector variables, also maybe much more complicated things. There's a lot of stuff available in PLUMED, of course. Then you can actually use, for example, the PLUMED driver, or you already do it immediately during the simulation in the stable states, and you print out these collector variables. And then you measure the averages. So the average in the space of these collector variables. So if your collector variables are 3 distances, say, just measure what is the average of each distance, and then that pinpoints the starting point of and the end point of a path, right? Now, how do you choose your initial guess path? Well, in the examples that I showed so far, we always use a linear interpolation, and that's very easy to do in the input. You can just say gen path, and you just tell it the beginning and the end, and it will just point a bunch of nodes in between. You just have to tell it how many nodes, and then it can even put some nodes on the left and on the right, some trailing nodes if you want. But maybe you want to do something smarter, and you can either construct it by hand, or, for example, maybe you already have a trajectory. Maybe you did a high energy temperature or a steered MD, or you somehow you are lucky and you have a trajectory that goes from A to B. You can actually use the PLUMED driver, and I will show you. I will go into that a little bit, maybe on one of the next slides, where you just optimize a trajectory. Sorry, you optimize a path CV using a a previous trajectory, right? So you just one trajectory, and you can measure on each frame of this trajectory the value of the collective variables that you use as arguments, right? So the space of collective variables that you want to use, and then you can just use that to make a guess path for your path CV calculation. Of course, you have to choose the number of nodes, and you have to decide if you want a trailing nodes, yes or no, and then you have to choose your biasing method. So how are you going to bias your simulation? My favorite methods are umbrella sampling and metadynamics, but of course you can use whatever you want. There's all sorts of examples, and I will show you a bit more. Are you going to use multiple walkers? I would say that's always recommended, but maybe you need a big computer for that. And then the things to do is, monitor path evolution and convergence. So how does the path move? Does it move in a healthy way? And I'll tell you in a second what I mean by a healthy way. And of course, monitor the free energy evolution and convergence. And for example, if you use metadynamics, then maybe I refer to you to this recipe that I showed you in the beginning. It's an old paper, but it's still useful, I think, where you can look at the dynamics of the free energy landscape and see if there's no hysteresis, if there's no spikes, are things converging? And also in path metadynamics, you should monitor the free energy. And if you use another method, for example, umbrella sampling or steered MD is a good one. If you move from the left to the right, it's easy to monitor if you have hysteresis. So it shouldn't matter if you go forward from the reactants to the products, or you pull backwards from the products to the reactants. Of course, the final result should be the same. And if you have hysteresis, then clearly something's going wrong. And then there's other features that you can add, such as a tube potential, and also in the exercises you will be asked to think about using a tube potential. So what does a tube potential do? A tube potential is basically an extra potential that works on the path, orthogonal on the path, so this so-called Z direction, so the distance away from the path, to make sure that you stay close to the path. Now, why would you want to do that? In principle, it's not a good idea because you limit the sampling of the width of your channel, and that could have an entropic effect that maybe is important. But sometimes you need to do it because maybe there are side reactions that you would go otherwise in that hamper your sampling, and then you have to limit it. And there could be other reasons why, it's sometimes a good idea to use a tube potential to have a better behaving sampling. That will be discussed also in the exercises. So which biasing method should you use? Well, as I said, my favorite is metadynamics and umbrella sampling. Of course, if you use metadynamics, then there's all sorts of features, such as well-tempered metadynamics, that you can use, which is really nice, right? So well-tempered gets you better convergence. I must say, actually, I don't use it so much. I prefer to scale my Gaussians by hand, but why should you? You can also have it done automatically. Constraint MD is a very nice method as well. Then the method starts to look more like the string method, let's say, but also steered MD, right, as I said. And then there's methods that I personally haven't used, but I think they're very powerful, and I would very much, advertise them. And finally, an interesting one is transition path sampling. So even if you generate paths that go from A to B, trajectories, you can get like an average over those trajectories, right? And so if you have to do transition path sampling, where you sample from one interface to the next to get rates, and you would like to have a good description of these interfaces, and it could actually be a good idea to use a path collective variable to define your interfaces. So I understand that I'm brief and you may not quite understand what I'm talking about, but feel free to ask me later if you want to know more about how to use path collective variables for transition path sampling. Okay. How do you obtain a guess path? Well, as I said, we usually use an linear interpolation, or you can do a guess by hand. If you make a guess by hand, the thing is that, even if you just decide, I'm going to take a bunch of nodes, one here, one there, and you just write those numbers up in the input file, as soon as you start the simulation, the first thing it does is reparameterize your path to make all the nodes equidistant. because this is necessary to be able to guess where you are between 0 and 1, right? So the nodes should be equidistant. And it will do that for you, which means that it will change your path a little bit. Or you do that, you make sure by yourself that they're equidistant. Then, of course, it's not a problem. In any case, it's not a problem, but you should just be aware of it. And as I said, the other way to do it is use the Plume driver, and you just feed it a reactive trajectory. So some trajectory that went to A to B, and you can actually use the Plume driver to optimize the path. Since the path has to converge a little bit, the way to do it is actually just write a little script where you feed the trajectory many times, maybe 10 or 20 times or so, every time the same trajectory until the path doesn't converge and it doesn't change anymore, and then you're done. But fine, it's a simple trick, and it gives you a nice initial path. Okay, so how many nodes should you choose? Well, not too many, not too few, I would say. So what is a good number? Well, in this example of the polyproline, the purple line is, of course, too few, all right? So not enough nodes, you get a very crooked line. If you use too many, this is the blue one here, you may get all sorts of wiggles that are due to the limited statistics, maybe in certain parts. And that's also spurious, right? So it's like overfitting, basically. And so if you see this sort of wiggles, then yeah, you probably have too many nodes, right? And so in this case, the green one would give you the best path, I would say. Okay. Yeah. About how many nodes? Well, not too few, not too many. It could be good to rescale the collective variables, right? So if you define a path in a space of collective variables, and one is a distance that runs from 2 angstrom to 3 angstrom, and the other one is an angle that goes over 360 degrees, then you have a very strange space, right? So if you would draw it on the same scale, it will be very stretched, and it could be that that determines the shape of your path, because it uses Euclidean distances to measure each distance to the path in that space. So so if I have a two-dimensional space, and on one axis I have an angle, and on the other one I have a distance, then measuring a distance to a node, if I'm somewhere in this space, I'm running a simulation, at some point I'm somewhere in this space, so the distance has a value, the angle has a value, and I want to measure the distance to the closest node. It may, that distance, whether the distance has the largest component, the largest difference in the direction of the angle or in the other collective variable, may depend on the dimension of my collective variable. So if I would change now from degrees to radians for my angle, or from angstroms to nanometers, this distance may suddenly turn out to be completely different, because I'm stretching the space in one collective variable or the other. So the way to fix that is to rescale the collective variables. And so, for example, you could say, oh, my distance just moves from 0 to 10 angstrom, so I'm just going to divide the whole thing by 20. What did I say? From 0 to 10, I divide the whole thing by 10. So then the distance goes from 0 to 1, right? And I can do that for all the collective variables, divide them basically by the length, the span from minimum to the maximum that you want to sample. And then all your collective variables go from 0 to 1, and you can very easily do that with the combine directive in PLUMED. So if you're worried about strange scales of the collective variables that span your CV space, then it's a good idea to rescale them. Most paths and free energy conversion problems are due to an incomplete collective variable description of the transition, right? So of course, you need good collective variables. Second cause of problems, the path is too flexible, and there's things you can do about it. And so what can possibly go wrong? Well, as I said, if you miss collective variables, then convergence will be a problem, and you have an incomplete description of a transition, and you should go back to the drawing board and see what other collective variables could be important. If your path is too stiff, it doesn't move enough, then you should add more nodes. Should make a longer path, or add more nodes to your path. If it's too flexible, then reduce the number of nodes or add a tube potential to stay close to the path, or gather more data before you move a node, right? So don't update so often, but get a good estimate of the distance along the path before you move the nodes, or get a better guess path, right? So there's several things you could do if you notice that your path is too flexible. And another thing that could go wrong is that you update your metadynamics potential if you use metadynamics. For example, much slower or much faster than the path update. It's usually not really a big problem, except that, well, you could have done it faster probably. Maybe you're not so efficient because your potential is already updated, it's already perfect, but your path not, which means now you have a perfect free energy profile, but along a path that is not relevant because the path is still moving, right? Or the other way around, your path is already converged, but you're still waiting to optimize the free energy landscape, and you could have probably done that faster. So this is not really a problem. It's just that, well, you could have been more efficient. This I'm going to skip. And then final notes about the exercises. So you will see that there are 5 exercises in this masterclass. They are available in the PLUMED website. I hope that everyone sees them. They have, if you download them, then you can download them from GitHub. I'll show you in a second how to do that. And you will see that you will see 5 directories with that correspond with the 5 exercises. The first directory is called 0MD. It's just an MD simulation. Then the second one is called Metadynamics. So first you have to do a 2-dimensional metadynamics. Then we will do path metadynamics, but with a fixed path. Then the 4th exercise, now we will do an adaptive path. So we will optimize this path. And the final exercise is do it with the multiple walkers. So these are the exercises. To do those exercises, you have to do a git clone. Basically do this command, but that's all described on the website in Plume. So if you go to this masterclass HTML file, you will see this. And I can quickly show you. So if you let's say let me open a new browser. So I go to plume.org. We're here. I go to masterclass, right? And oh no, I should go to manual, I think. I should go to the doc, of course, here, the manual, and I think it's for this version. Is that true? Tutorials. Here we are. 22.9. This is the last one of the 2022 series using path collector variables, and aims, objective, prerequisites, and here setting up the software. You run this git clone. Okay, so that's and then you'll have your local version with these exercises. It also comes with its own plumed version because some files I've adapted a little bit. In particular, we have our own developed path CV version that's developed in our lab, which has the multiple walker stuff, which I don't think is yet in the official Plumed online. Feel free to use the version online. So if you want to use a more recent version, there's Plumed 2.8. I'm more than happy to help you as well. Some commands have changed a little bit, but that's all fine. If you don't want to have really zero trouble, then I recommend you to use this one. It takes about 5 to 10 minutes to compile it, and then you have your own local version with the local manual as well. Final note. If you think, oh, but this is all too easy for me, because this is actually working on a relatively simple potential, so no molecules involved. And this is the famous Muller-Brown potential with 2 collective variables, and there's 2 minima here, and maybe a small minimum there as well. And we have to find the path here and get the free energy profile. If you think, well, that's too easy, I really invite you to try your own molecular system with your own favorite molecular dynamics software, like GROMACS or NAMS or OpenMMM. You can also try out Alberto's plumed nest files, with the multiple walkers for the polyproline, for example. This one is polyproline, I think, or no, this is DNA. This is polyproline. There's also alanine dipeptide. So feel free to try these more advanced exercises. They are not described in this list of exercises, but you can do whatever you want. This week I'll be on the Slack channel. I hope to see you there as well. Probably not so much during the day. I may have a peek, but usually I will probably answer in the evenings. But if any questions, then feel free. I'm here to help, and I'm also here to learn actually about your scientific problems and your interesting ideas. And yeah, I'd be more than happy to discuss with you on Slack or anywhere else actually. So with that, I think I want to close. I'm not going to talk about machine learning now. Let me one more time acknowledge the people that did most of the work that I talked about today, which is Rakesh, Alberto, and Ambush. And that wraps up this masterclass, at least the first session. Of course, next week there's another session where we go through the answers, the solutions of the exercises, and also answer all the questions that you still may have. And with that, thank you so much. At the end, I put a bibliography because I mentioned many methods and ideas, and these are the papers that you may be interested in. And as I said, I will post this online on this GitHub page. So this GitHub page, this is my page, which should be somewhere. Let me see. How do I get here? Yeah. Anyways, I will put it on this GitHub page, so you will also have the slides. Okay, that's it. Any questions? Let me stop sharing so we can see each other. Feel free to switch on your camera, then we can say hello to each other. And if there's no more questions, hey, Albert, nice to see you here, man.
Nice to see you too. Thanks for the masterclass. It's super interesting.
Very welcome. I was thinking to talk 1 hour. I talked for well, we started late, of course, but I talked for more than 1.5 hours. Anyways, was more to tell you than I thought. I see also Simone. Do you have any questions, Simone? Oh, I can't hear you, man. You're mute.
Sorry. No, good lesson. Thanks, Professor. No questions.
No questions. Good. I hope things were a bit clear. Are you gonna try the exercises in the coming week? Are you gonna have a go at it? Okay. I think we are all tired, ready for lunch, or at least a beer or something bubbly before lunch. I would recommend. And then I hope to see you on the Slack channel, everyone. And I wish you a nice evening, and next week there will be the solutions. Bye, everyone.